So this video is going to go over the PowerPoint for the Earth's interior. So I'm just going to kind of blaze over some of the slides and try to explain some of the things that I would do if we were in person. But I'd still like you to look through the PowerPoints. And of course, if there is any kind of links, you can go view those and it'll kind of expound on what we're trying to illustrate here in the slides. So the basic idea is we need to know what's going on inside the Earth because that impacts what's happening on the surface. And the two main components we want to understand about that is what's happening in the interior, which we'll go over this week, and then plate tectonics. And we'll see that those things are related, and of course they're driving lots of the hazards that we want to talk about throughout the semester. Okay, so the main thing that we look at when we talk about what's going on inside the Earth is we look at compositional differences. And so we can break it down how the Earth looks in a bunch of ways, but for this part we're going to say it's based on the composition. That's kind of the easiest way to do that. And what we have here is what's called the crust, the mantle, and the core. And so the crust is an extremely thin layer that's here at the surface. The mantle is very thick. It runs from the bottom of the crust all the way down to here. And then we have a core, which there are two parts to the core. There's an inner and outer core, but we're calling it all the core because it's basically made of the same stuff. It's just in a different phase. And what that means is the outer core is an iron nickel rich composite, and it is actually a liquid. It is hot enough down there. As we go down in the Earth, the heat increases. And although pressure increases also, the temperature there is basically winning out over the pressure increases, and so it remains a liquid. But as we keep going deeper, although the temperature does rise, so does the pressure, and once we get to a certain depth, the pressure wins out over temperature. And the inner core is actually solid, even though it's made of very similar components. Okay, so crust, mantle, core is the way we can break things down compositionally, but that is not the only way that we can do that, of course. So what we want to do is look at something a little different. And this comes into play when we talk about plate tectonics, but we can look at how the materials behave. And what does that mean? Well, it means for us mostly whether it breaks when we apply pressure or if it flows and can move almost like a liquid when we apply pressure. And so based on its properties, we can break down the Earth into different components. And so what we want to see here is something called the lithosphere. This term applies to the brittle part of the Earth. And now it does include the crust that we just talked about, but it also includes part of the mantle. So the idea is that the temperature as it increases as we go down inside the Earth has not increased enough to cause part of the mantle to be what we call ductile, or the ability to flow. And so it's still cold, and it still reacts in a brittle fashion. And so you can see from this image here, there's a little bit of crust here, and this part is the mantle, because there is a compositional difference between these two, but they both behave the same way. So we're going to group them based on their behavior, which is that they're brittle. Now, I did fib a little when we talked about composition in that there are two types of crust. There's what's called the oceanic crust, and that is the crust that's mostly beneath all the oceans around the world. And then the continental crust, which is mostly the crust that is above sea level, though that's not always true. The continental crust is thicker and made of slightly different components than the oceanic crust, but it's still different than the mantle. So there still is a compositional boundary at the base of each of the crusts. Doesn't matter if it's oceanic or continental, there's still a chemical difference. So we can still say, oh yeah, compositionally, crust, mantle, core. When we do the whole behavior thing, properties, we're just going to say that everything, either crust and part of the mantle here, behaves in a brittle fashion. And so we're going to call that the lithosphere. Okay, so that's how we're going to break apart the differences there. Now below the lithosphere, we get a different behavior. And so, oops, let me go back. Sorry about that. So the different behavior we see here is what we're calling that ductile property. And so as we go beneath the lithosphere, there's a boundary here. And even though it's the same composition, it starts to behave different. We call that the asthenosphere. And it has the ability to flow, but it's not a liquid. So we don't want to say, and you may have heard someone mention this or in whatever you're getting your information, that there's a whole bunch of magma flowing around inside the Earth. That is not true, right? So the inside of the Earth and the mantle is hot and it can flow, but there's only really tiny places where there's molten rock inside the Earth. The overall mantle, when we get below this depth of the brittle lithosphere here, this asthenosphere, can move, but it is still a solid. So think about like silly putty or maybe even some Play-Doh or clay of some kind, right? That when you apply pressure to it, you can change its shape without it breaking, right? So it flows, it moves. We're talking, rates that are centimeters per year, 5, 10, maybe, centimeters, maybe 15 at the most, centimeters per year, for a long year, right? A couple of inches a year. So that's very slow motion. But it does move. So when we apply pressure to it, it doesn't break. It actually is going to flow. And that's the behavior that's separating the lithosphere from the asthenosphere. Okay, so I'm going to try and put it all together because it might seem a little weird that we have all these components, and it's really the mantle that's causing trouble. So the idea is that when we look at our Earth, we have all these layers here that we've discovered, but it's the mantle that's behaving differently, and that's helping us break out different parts. And it's really just based on pressure and temperature. As we get deeper in the Earth, heat increases, and heat on its own wants to change things from a solid to a liquid. As we heat things up, they get hotter, the molecules move faster, they move farther apart in general, and so we get a change of phase from a solid to a liquid. But pressure wants to do the exact opposite. As pressure increases, it doesn't want to cause the molecules to move apart. It's actually crushing them, pushing them together, making them a solid. So as we go down into the Earth, there's this battle between heat and pressure. And depending on where you are and how much heat and how much pressure, sometimes pressure is winning the battle and sometimes heat is winning the battle. When pressure is winning, it's usually solid, brittle. As temperature starts to win, we get this more ductile behavior, and eventually we can get it into a liquid, which, remember, is what's happening in the core here. So these are the same compositions, but the temperature wins in the outer core, it's a liquid. The pressure wins in the inner core, it's a solid. Okay, but if we look at this diagram real fast, we can see that the crust is the thin part at the top, depending if it's ocean or continental. The ocean crust is thinner, continental crust is thicker. But then we jump into the mantle. The mantle is all these things. It's this kind of brownish, and the orange, and then the red. That's all mantle. But it's behaving in 3 different ways. Toward the surface, it's part of the lithosphere. It's brittle. Right beneath that, it's the asthenosphere. It's this layer here. That's the most ductile part that can flow and move. And then below that is the mesosphere, and we don't really talk about that so much because when we're talking about plate tectonics, it's really about what's up here. And this is still has the ability to move and float, just not to the degree that the asthenosphere does. And so there's still some speculation on how these units or layers interact, even though they're similar composition. So what I want you to take away from all this is crust, mantle, core, composition, and lithosphere, asthenosphere is a behavioral difference, a property difference. And that's how we want to break those down near the surface. Okay, so how do we know all this? Well, we drill, right? We drill into the Earth, we can sample some things, and we can learn some things about the Earth. The problem with that is we certainly haven't done that. The problem is we can't drill very deep relative to the size of the Earth. And so when we look at some of these things here, some gold mines, some pits, some oil wells, some attempts to reach deep into the Earth, this is the crust of the ocean. It's about 7,000 kilometers thick. And here's the continental, maybe on average 30. that there's a range for both of these, you can see that nope. And here, we're in Oklahoma. All right, we're not here. We're on this one. So we didn't make it. Same thing with Russia. We're not in the ocean. We're in the continent. So these two have never, and in theory, we've never anywhere on the Earth been able to drill through the crust, whether it's oceanic or continental, and sample the mantle. And so we don't know what's down there because we've never been able to grab a piece of the mantle. And so, of course, if we're thinking, well, maybe we'll go to the core, holy crap, now you can see we're even worse off. And so there's an attempt to get to the mantle, and there was an attempt in Russia when they drilled this hole here. There's an attempt to drill in the ocean basin when they did this here. So you could take a quick look at those and learn about how we've attempted to get to the mantle and some of the problems we've run into. So what that goes back to is, okay, so we've never sampled anything besides the crust, ocean and continent. So how do we know there is a mantle down there? How do we know there's a boundary there? How do we know there's a boundary below the asthenosphere? How do we know there's a boundary between the mantle and the core? Well, we use earthquakes. And so we will certainly talk about earthquakes and talk about their hazards and all the things that come with that. But for now, we're just going to talk a little bit about how earthquakes radiate the energy. So when there's a breakage in the brittle part of our lithosphere, energy is released from that, and that energy propagates out in all directions. And so we can record that through seismometers, right? We have instruments that can record the energy that's coming off of that. And today, of course, we have thousands of seismometers all around the world. And how that energy in waves moves through the Earth can tell us something about the Earth. It's almost like an X-ray of the Earth. And so really briefly, we're going to use seismic waves to figure out what's happening inside the Earth. Now, we're not going to get into all the gory details, but I just want to cover a couple things really fast, and that is there are two main types of waves that we want to focus on really fast. P waves, sometimes called primary waves. S waves, sometimes called secondary or shear waves. These waves are generated from an earthquake and can be picked up by our seismometers, and they travel throughout the planet depending on how big the earthquake is. It's useful to know some basic properties of the waves, and the really key here is this second part. P waves are fast, and they move through both solids and liquids because they transmit their energy through compression. So they move through any phase material, whether it's a solid or a liquid, doesn't matter. Okay? For our secondary waves or our shear waves, they're a little slower because they actually have a shearing motion as they propagate through the planet. What that means is they cannot go through liquids. They only go through solids. So we can use that information to understand some of the phases, if you will, of the material that's inside the Earth. So look, when we have an earthquake, we have waves that propagate out, right, all in a circle here, but the wave front is moving along until it hits something different. Now, if it's different composition, we can get a reflection off of that. If it's a different behavior or properties, we can still get a little reflection off of that. And then some of it goes through, and so some of it gets refracted. And so the bending of the energy waves and the bouncing of the energy waves tell us that there's a boundary there. Something's changed that's caused this energy wave to either reflect or refract. And so that's one way that we can determine that there's something different down there. Whether it's a behavioral change or a chemical change, we can use these energy waves from earthquakes to paint a picture of what's happening inside the Earth. So that was the one way that we figured out that there was a crust-mantle boundary, because there's a compositional difference between the crust and the mantle. We could see this change based on how the waves were being received at our seismic stations. And so you can read more about that if you'd like to there. But same thing, we don't want to get into the gory details. We just want you to understand that we're using these energy waves because their speeds change depending on the material they're moving through, and they react to boundaries by either reflecting or refracting, and we can pick those up with our seismometers. Okay, so as we move through the Earth, we can see that this is kind of what is happening. Our velocities of our waves are increasing dramatically because the theory is the pressure is causing the material to be super compacted, which means energy can move through really quickly and efficiently. But we can see a dramatic change in speeds once it hits the outer core because the phase has changed. Remember, solid, liquid, a lot slower through the liquid than the solid. And we do see that S waves appear to stop. And we did say S waves cannot go through a liquid, so that would be an indicator that we have a liquid somewhere inside the Earth. So I'm going to run past these slides for a second. This is just an illustration of if we didn't have anything different on the inside, we would expect waves to do this. But we see weirdness, basically, and that weirdness is telling us there's something going on inside there. So we can figure out that there's a core through P waves, which are the ones that can go through everything. But it's a little easier, I'm hoping, for you to understand how we can use S waves. So in this example here, remember, S waves cannot go through a liquid. And so we have seismometers spread around the entire world. Today there's thousands, right? An earthquake occurs. And so all of these seismometers are picking up the S wave. They're telling us there was an earthquake and the energy has reached my seismometer. And it's given me a little, wiggle on my line here telling me that there was an earthquake. But there's a component, a part of the Earth that receives no S waves, even though they can receive some of the P waves. So they know there's an earthquake, but they're missing one of the waves that is generated by an earthquake. And so the suggestion from that is that there must be something down inside the Earth that's a liquid that's stopping these waves from moving through. And we can also determine the size, because imagine if this core was a lot smaller. If this is the liquid portion, then I would have what they're calling a shadow zone be much smaller. And so based on the size of this shadow zone, we can estimate the size of this liquid that's down there, which would mean I could start to get some dimensions about the diameter of this inner core here and where this boundary is at depth between the mantle and the core. And of course, we can do much more things with all these waves because the S waves can move completely through and give us some data. And their speeds change, which tell us something about the solid inner core. We don't want to go too much into depth with that. I just want you to have the general idea that we're understanding a lot of the interior of the Earth based on what we're going to call remote sensing, really. We haven't been able to go there, so we have to use other methods to see inside the Earth. And seismic waves is one of the big ways that we do that. All right, so hopefully that kind of makes sense. So we're going to jump over here. How else do we know what's inside the Earth? We can use gravity. And so we can calculate gravity, the force of gravity, and it's based on distance and mass of objects. And so what we can see is there's some ways that we can figure out the pull of gravity and measure it, whether it's if you're closer, then you have a stronger pull. If you're farther away, it's weaker. We can also determine that the more massive objects are, the stronger, the less massive, the weaker. So here's an example of our little gravimeter. It can be used to determine things a little closer to the surface, but it's still a way to look inside the Earth without drilling. And so it can be a way to find maybe deposits that are heavy, that have a lot of metal in them, some ore deposits, or even finding open spaces, caves. So we walk around and we take measurements, and then we can determine that there's an anomaly somewhere. It's either giving us a higher or lower reading, and that could tell us something about the interior of the Earth. And so we can use that for big structural things. We can use it for certain rock types. A lot of times we can use it, like we said, for deposits of things. Ore bodies and things like that is useful. We can also use it for structural things. So here's a fault, an old fault that's buried, which we couldn't see at the surface. But we would have a gravity anomaly over there because the material here is different. More massive over here, less massive over there. It could tell us that there's something hidden down there, right? So we can use gravity to figure out what's going on. So that's kind of useful. And the last thing I just want to touch on before I let you take a break is the Earth's magnetic field. And so this diagram here is a typical one you'd see with a bar magnet running through the planet. But of course, our planet doesn't act exactly like that, but it's a general idea that there is something happening inside our Earth that's generating a magnetic field where we have what are called force lines that come out of the South Pole and kind of come back into the North Pole, much like a bar magnet would induce if we could lay one out on the table and take out our compass or measuring device. We could measure the magnetic field around a bar magnet, and it would look very similar to this. And so when you're on our planet and you have a compass, it's pointing to the north because the lines are emanating out of the south and going into the north. And so our magnetic North Pole is up to the north there. And so what do we think is happening here? Why is this happening? Mostly the explanation is that the iron-rich core is generating our magnetic field. So look, when we move iron, it has a lot of electrons in it. We can generate electricity, which can generate a field. And the idea is that because the liquid outer core is moving differently than the solid inner core, it's convecting, it has motion. But in general, it has a kind of, when we add up all the vectors, it has a motion in one direction. And that movement of the iron over the iron is causing a magnetic field to be generated. And so that's the current kind of idea for why we have a magnetic field. And we can test this in the lab, you know, with different materials and iron-rich stuff and liquids and solids and say, hey, look, we did generate a magnetic field and it seems to match the density of the Earth and all the boundaries. And so but once again, we haven't, you know, sampled that. We haven't seen that, but that's the explanation for why we have a magnetic field. Now, when we look at maps and stuff, which we're doing, remember that the geographic North Pole, which is where the Earth spins around that imaginary kind of axis, is not the same as the magnetic North Pole. So when you grab your compass and it points to north, it's pointing to a magnetic north and not the geographic north. And so sometimes we'll have to make an adjustment if we're looking at a map, because all maps are made with the geographic north in, you know, to the north and not the magnetic, so we have to make some adjustment there. There has been some evidence that we've seen in the rock record that suggests that the magnetic polarity has changed in the geologic past, whereas today the magnetic force lines are emanating from the south going into the north, but in the past they kind of went the other direction. And so we can get that from our rocks. Our rocks, in particular igneous rocks, think of lava, right, molten rocks, because they have a lot of iron in them, they make magnetite, and magnetite will align as it cools with the magnetic field. Think about it as a little compass needle. And so when we sample the rock, we can see that all the magnetite crystals are lined up in a certain way. And we can say, oh, look, here we found some lava, erupted yesterday. We measure it, it's aligned with the current magnetic field. But we find older stuff that's the exact opposite, saying that potentially something has changed and the alignment is opposite, suggesting that the magnetic field was opposite. And so we found that at some ridges, so it's not super important that you kind of get into this. We're going to go crazy on this plate tectonic stuff next week, but just an idea that this is kind of where we found it because it's a place that has constant eruptions at these mid-ocean ridges here. And this is where we measured the change, the difference in what we call polarity there. All right, so we're going to jump through that. All right, that's just crazy. So, this last part I think I'm going to save. So you can view this if you'd like. It's a little video about more seeing inside the Earth. We talk about how do we know what's happening, and earthquakes can tell us things. I'm going to show you this in the plate tectonic
Quake activity
here,
beneath Cook Inlet, southwest of Anchorage, Alaska.
Earthquake locations, right? So here it's plotting the epicenter, and the epicenter is, you know, the surface expression of an earthquake here. And so what it's showing you here is that this is a plate boundary between two plates here. And so there's some weirdness in that there's deep earthquakes on one side and no deep earthquakes on the other, which is kind of strange. And to try to figure out what's happening here, we can use a side view. So if we look at the side view here and say,
quake
what does that
activity
look
beneath
like?
Cook Inlet,
When we plot
southwest
the
of
location
Anchorage,
of the
Alaska,
actual
clearly
rupture
shows
where
the
earthquake
inclined
actually
fault
broke the
plane
rock,
separating the
we
North
can see
American
that
and
this
Pacific
is why
plates.
this one side over here had deep and this didn't. It's suggestive that there's something going on, and this happens to be another plate boundary that you'll be introduced to next week. But in some cases, when we have plates that are moving around the lithosphere and they run into each other, in some cases, some parts of the lithosphere actually get pushed down into that silly, putty, gooey asthenosphere because it can move. And the gooey asthenosphere is not brittle, so it doesn't break. But the lithosphere does break. And this is one way to see inside the Earth, where we see that this material that's breaking must be different than this material and this material that's not breaking. They're all under stress, so why does this break and this doesn't? The suggestion is that this is brittle and this isn't. And so that could give us a change or a boundary or something that we could determine is different inside the Earth without actually going there. All right, so we'll do more with this in the future. Next week, you'll kind of see this again, and hopefully it'll make a little more sense, but it's just an example of how we see inside the Earth without actually getting there. All right, maybe that's it. Oh my Lord, there's more, you say? All right, same thing. We won't worry too much about this. Just another way we can use, here we're using temperature. It's almost the same thing I just showed you with the earthquake locations. Colder, hotter. So why is this colder? Why is this hotter? If we take something that was near the surface that's colder and push it down into this hotter stuff, it takes time for this to heat up. And so there's a temperature difference. Another way we can look inside the Earth without actually going there, right? Oh my gosh. So here's some other links. You can kind of check it out to learn a little more about that. Hopefully that's helpful for your lecture quiz. Remember, you do have a, PDF that you can look through that explains a little more detail about the interior of the Earth and some rock types and things like that I want you to look at. So make sure you check that out as well as this before you take the lecture quiz. All right.